So today's lecture is the final one that I want to do on GANs, and this one is focused on two things. First is what I call image-to-image GANs, right? So kind of what we've been doing so far is a situation where we have, we've got some sort of latent space. And this is often basically like random noise, right? We put that through the generator, and what gets produced is usually an RGB image, right? But there have also been a lot of GAN innovations of the form, basically, I put a image in, and what I get is an image out that's the same size. So the idea is that the input image is like guidance to produce the output, right? So for example, I could turn a photograph into a painting, or vice versa, or I could turn a sketch into a image, or I could turn a daytime scene into a nighttime scene, right? So the idea is that, I kind of want to, transform the input image into the output image. And so this is kind of similar in some sense to, kind of like, what I'd say, if you remember lecture 2, we talked about things like image analogies. Image analogies were the kind of thing that, for example, I could do like this paint by number application where I could, kind of sketch, okay, I want this to be land and this to be trees and this to be water, and that would generate an image, right? It was doing that with pre-deep learning techniques, right? But a lot of these, image-to-image GAN things are doing that type of thing, but better. And so I'll show you some of the results. Okay, so I really want to talk about 3 major innovations in this image-to-image space. And so the first one would be what I would call conditional adversarial networks. And the reason it's called conditional, I'm just going to see if I get better focus here, is it's basically conditioning on, I've basically got my usual, there's still some noise input, but there's also an input image X. These both go into the generator, and what comes out is an output image. And so I'm thinking about Y as a generated image that is produced by both X and Z. And so kind of the exemplar of this type of thing is a paper/algorithm called pix-to-pix, okay? So pix-to-pix is a famous algorithm. This was by Isola et al. And group from Berkeley in 2017. The original paper was not called pix-to-pix. It was called image-to-image translation with conditional adversarial networks. But I kind of put AKA pix-to-pix on the on the website because that's what everyone calls it. Okay, and so how does this work? So this is the generator, right? And then the discriminator is considering both the input image and the output image when it's making a decision. So basically, I have X is my image, and Y is my another image. So it's kind of like saying that Y is like a output. Sometimes I'm going to call it like a candidate image, and X is my input image, just to be clear. And these go through a discriminator, and the discriminator basically gives it a score in 0 to 1. So again, I think about this like a score that is based on both X and Y. So kind of the way to interpret this is like saying, well, how harmonious are X and Y together as a pair, okay? And so before I go on, let me just kind of show you some examples of like what do we mean by X and Y, right? So here is just some examples from the original pix-to-pix paper, right? Where my input image in the upper left could be like a paint by number segmentation of saying, okay, I want the purple to be street, and I want the blue to be cars, and I want the green to be tree. And then the output is this, RGB image, right? Or I could pair, like satellite view from Google Street Maps and kind of like, map view from Google Street Maps. Or I could do something like black and white versus color. Like I could use this network to do colorization, right? Or I could have the same image that I took at daytime and nighttime. Or I could take the edge image that I could create using, if you take image processing, I can look at the edges of an image and then look at the output. And the advantage of all this stuff was that these paired images are all generally not that hard to obtain, right? So we know that there's been great advances in segmentation in computer vision for quite a while now. And so taking an original input image and then doing the segmentation and then feeding the segmentations and pairs into the network is not a hard thing to do. You're not really doing extra data collection to do that. Similarly, like getting the edges of an image is just like one line in Python or MATLAB, right? So it's easy to get this. It's easy to take a current color image and make it black and white. So this was something where it was not that hard to create the x, y pairs, okay? And so once we have this kind of idea of paired images, then we can make some reasonable objective function, right? So kind of like the conditional GAN objective function looks something like, I have one kind of GAN-based loss that is, again, between the candidate generator and a candidate discriminator. How good is this pair? Well, I have a couple of terms. I have one term that's basically saying, how good is the discriminator, right? So for real images, this D should be outputting 1, right? So this is like for real images, D equals 1, hopefully. And then I have the generated images that come from X and the latent variable Z. And again, I want to discriminate those. And what I want here is this. This is like saying, fake images. I want D to be 0, right? So kind of what I'm doing is instead of feeding with an original pair XY, I'm feeding it instead with X and whatever comes out of the generator, right? So this is a fake image. So G is trying to minimize this thing, and D is trying to maximize this thing. So the same kind of trade-off between this minimax problem where they're trying to compete against each other, right? And then, in addition to that, there is another loss that the authors added, which is basically this L1 loss just on the generator that is basically taking all three of these things and saying, I want to minimize the difference between the generated output image and the real output image and the generated image, right? This is basically like saying, I want to make the real and the generated outputs close. Which stands to reason, right? I want the generator to be making things as if they're like real XY pairs. So one thing that was noted about this algorithm in general was that unlike the VAEs or vanilla GANs, where the Z, the latent variable, has this huge effect on what image you generate, here the Z is kind of like more akin to dropout in the sense of it's adding a little bit of noise to what happens in your output, but the results are not usually that random coming out of this conditional GAN. So basically it's the input image that you put in that has the most effect on what you get out, and then the Z will play a role in making like little bitsy changes in the output, right? So you don't always get exactly the same result every time, but you're not getting like crazy different samples as you sample from this conditional GAN. And so there were a few other under the hood architectural innovations in Pix2Pix that also kind of propagated through into the literature. So one key thing that was important here, and honestly, I'm not sure, I don't think this was the first place to do it, but this is one of the uses of what's called the UNet architecture, which you may have heard of if you ever looked at like stable diffusion and stuff like that, that also uses a UNet. So I'm going to defer discussion of what this means until we talk about it later on. But basically, just to say it's like a slightly different architecture. One thing I will mention in passing is that they use also something that's called a patch GAN discriminator. And that was a kind of a good innovation in the sense of saying that, typically when we talk about the GAN discriminator, it's operating on the entire image to produce a 0-1 decision, right? Instead, what was going on here was that we took the output image and we split the output image up into a bunch of, overlapping patches, right? So I kind of like am taking chunks of the stuff I create. I'm using different colors to indicate that these patches are going to overlap, right? And then what we do is, we put, patches into the discriminator to get a result, and we average over all the patch scores. And so these patches, for example, might be like, 70 by 70 pixels. At least that's what I have in my notes. I'm not sure why it wouldn't be something more like 64 by 64. But anyway, so the idea, or maybe it was that they were using 70 by 70 patches over the whole image. But the point is that each of these patches is relatively small, and I'm making a discriminator that tells, like, is this patch consistent with, what I saw in the training data? And this means that the discriminator can scale a lot better, right? Because I can always take whatever huge image that I have and tile it up into these smaller patches, and I just average the patch scores as they go through the discriminator. So, that was another advantage that was good. Okay, and then the cool thing was that, this is another example of, again, I don't remember exactly the timing, but you may know that there is this, kind of like, when I was a grad student, right, you submitted your paper to a conference, and you waited to get the reviews, and then you got the results, and maybe once the paper was accepted, you put it on your web page, right? But of course, this was before, like, I'm not saying it was before the internet, but it was certainly in the earlier days of the internet, right? And so now everything is on archive, right? So as soon as this paper hit archive, even before it was accepted for publication, people started to use it because the code was out there, right? And so the code was also used in ways that I think the original authors, didn't really anticipate, right? So there was like this whole process of like turning an edge map into a cat-shaped object, right? Edges to cats. They used it for background removal. They used it for turning a sketch into a Pokemon, right? And so again, just by training the, kind of pix-to-pix architecture on different pairs, people made all these wacky results, right? And so now if you look on archive, you'll see that, the archive version of the paper, and maybe even the paper that eventually got published in the conference, kind of pays tribute to all the people that started to use their code before the paper acceptance was official. And so and of course, a lot of artists also started to fool around with this as well. And so in the second half of the lecture, I want to talk a little bit about what artists were doing with all these new off-the-shelf GAN tools. There's a very cool pix-to-pix example I want to show you. Okay, so let me pause and ask any questions or comments about this. Yes?
Yeah, so for this pixel-to-pixel architecture, I didn't see any parts where they introduced the noise during the generation. So we treat them almost like a deterministic mapping between the sketch to the...
Right, so the question is, where is the noise? So there is still noise in the sense that there is noise coming into the discriminator. So the Z latent variable is still some noise, right? So there's noise definitely in the generator, right?
Because I just take a look at the original paper and use the UNet the structure as the generator, right? So the input will be purely the image itself.
No, I think that in addition to the image, there is still some extra injection of a Z, right? I mean, we can check. So let's take a look for a second. So the question is, where is the noise in this process? So if we look at the original paper, so yeah, so this Z here, right? They are using noise, right? Yeah, random noise vector Z to output image Y, right? And so all they're doing is they're adding the X image, but it turns out the X image really dominates the generation.
So, like the way they introduce the noise is by like adding additive noise to the image, or?
Well, we can see the question is whether this. No. I take it back. So it's not like we're adding noise to the image. The noise is coming in as a separate channel into the generator.
So the shape will be exactly the spatial shape will be the same.
No, I don't think there's any constraint that the spatial shape of Z has to be the same as the spatial shape of X, right? So here, I'm not sure if the details are in the paper. Like where does it tell us what the size of the latent space is? As usual, sometimes you have to scroll down to the appendix to see like where the stuff is. No, I'm pretty sure, yeah, this is not like we're adding noise to the image, for sure not. We're taking the original clean image and then we're putting in additional noise vector that acts as a, randomizing thing. But I'm just trying to see where is the dimension of the noise. Yeah. Oh, okay. So they're actually just dropping out stuff, right? Okay. So it is literally dropout, not just noise. I mean, I think there are different ways to do it. Let me just say that. I mean,
so during so for the dropout, usually when you train like a classification model, dropout will be turned off once you will do the inference part, right? And then for this generation part, the dropout will always be on.
Yes, I think so. So the dropout is always active. You're always like turning off some stuff in the network, as far as I understand it. Yeah, like I said, I looked at this summer, so I don't remember exactly how it works. But yes, so it is definitely true that it is certainly more deterministic feeling than a GAN, for sure. But it's not entirely deterministic either, right? That's what this dropout, is doing, basically. But yeah, that's a good catch that it actually, I guess that the Z is not like coming in as a extra conditional vector. It's actually just like coming in as a randomizing dropout, which is kind of a strange way to do it, but whatever. Okay, so this is like number one of the things I want to talk about. And this kind of led to, although I don't know about maybe the timing was a little bit simultaneous, something called Cyclegan was the next big thing. And again, this was coming out of Berkeley Group in 2017. And so this is a similar idea of trying to do image-to-image kind of translation, as it were, except that, if suppose I want to turn a bunch of photographs into Van Gogh paintings, right? I don't have examples of original image and Van Gogh version of that image, right? I mean, maybe I could get some people to hallucinate that for a couple examples, but I couldn't get thousands of good examples like that, right? So the idea was, what happens when we don't actually have paired examples of X and Y? What can we do? Well, we can say, well, okay, I got a whole bunch of examples of photographs, and I've got a whole bunch of examples of Van Gogh paintings. Shouldn't I be able to do something with these large corpuses of data, even if I don't have the correspondences between them, right? So the idea here is that I have a source domain image X. I put that through a generator, and what I produce is something that's in the target domain Y, right? And these are both images, okay? And so what I want is that, certainly I want it to be true that the generator is going to produce images that are coming from the same distribution as the Y, right? So we want the distribution of G of X to be indistinguishable from that of Y. However, this is super under-constrained, right? We talked about in passing this idea of what's called mode collapse, right? So it could be that the generator learns how to make like the exact same Van Gogh image every time, right? And the discriminator would say, well, yeah, this looks like a Van Gogh image, but there wouldn't be any diversity in the output. There wouldn't be any sort of sense that the input image and the output image were connected in some way, right? And so the idea behind Cyclegan was to say that we introduce another kind of inverse generator, right? So we also make a generator that goes from the target domain, Y, let's call this generator F, back into the source domain. And so this is like saying, OK, now I'm going to convert Van Gogh paintings back into photographs, right? And then we enforce the constraint, and this was the key observation, of what's called cycle consistency. That is that when I take the inverse generator and apply it to the forward generator, that this thing should be about equal to x, right? So if I take my painting to the Van Gogh, and then I take it back to the painting, or I'm sorry, photograph to Van Gogh and then back to photograph, I should get the same photograph, right? And so in a way, it's kind of like we're learning two coupled autoencoders, right? Where I'm trying to make this thing such that when I put the original in, I get back the original, right? Via this shared intermediate domain. And so the cycle consistency was the key thing. So instead of training one generator, we're training two generators. And of course, we still need to have discriminators. So we also have two discriminators. Plus, we have to have the cycle consistency that says that everything kind of works out, right? So if I was going to write down what the loss function would look like, it'd be like saying, OK, I have, remember I have a generator for x, a generator for y, a discriminator for x, and a discriminator for y. And so my loss function looks like I have one GAN loss function for the, well, I guess actually I didn't have gx, gy. I had g and f is what I called it in my previous slide. So let's say it like this. So it's like saying that, I have a GAN loss that's saying I have the expected value of the y discriminator acting on these outputs. This is like saying I have real y. And then I have the fake outputs. So this is like fake y. And then I have a GAN loss for the reverse guy. So it's like saying I look at over the distribution of x, what are my fake, or I'm sorry, these are my real x's. And then I have my fake x's. Sorry, I called this f. And then I have a couple of terms that tell me about the cycle consistency, right? It's like saying I have try to get the f of g of x to be low. And I could call this like the one norm of this vector. And then I also want the other way to work too, right? So I have g of f of y minus y. I want that to be low. So this part is like the cycle consistency term. And so that definitely had a big impact on the both research community and also on the artistic community, right? So again, the original paper, if I just go back to my browser for a second, was called Unpaired Image-to-Image Translation Using Cycle-Consistent Adversarial Networks. But everyone calls it Cyclegan, right? And the results of Cyclegan were along this line, right? So this is the premise, right, is that if I want to turn a photograph into a Monet painting and vice versa, that I try to train two generators that do this, right? And so then, that kind of led to, if I want to turn horses into zebras, I learned something that turns a horse into zebra and then a zebra back into the horse, right? So, I'm always having these two paired generators that work in concert, right? And so that was kind of clever. And in some sense, also you get the second generator for free, right? So you kind of are learning how to translate between these two different domains, right? And in a way, I think that this is not dissimilar to some approaches to like machine translation, right? So you imagine that you want to take like an English sentence, convert it into a Spanish sentence, convert that back into an English sentence. The two sentences should be the same, right? And by training a network to do that, you've learned how to translate between English and Spanish and vice versa, right? So that was, again, 2017 was when that kind of came out. And then the final thing that I want to talk about, let me pause this. Questions or comments about Cyclegan? Which may or may not be, you might think about whether or not either Pix2Pix or Cyclegan would be something that might be fun to try for one of your homeworks or projects, right? This is definitely fun to play with. Is that a hand or a, yes?
So when you're writing the cycle consistency term, parentheses a little strange.
Yeah, okay. Well, okay, I guess that this probably should go out here. Is that what you're saying?
Yeah, and then also
Syntax error. Yes, fair enough. Thanks. Okay, other comments or questions? All right, so the third thing that I want to talk about is something called, Spade, which stands for Spatially Adaptive Denormalization. This came out of NVIDIA in 2019, but everyone calls this, well, okay, I shouldn't say it, kind of previously known as GAN, because GAN was an artist, and so it was a play on words, right? So kind of popularly known as GAN was this paper. And so kind of the idea behind this is this kind of neat paint by numbers GAN. And so the setup is basically like this, right? So you as a user sketch kind of like a colored, simple thing of, okay, I want there to be water here and grass here and trees here. And then there's also what they call style image that kind of controls what do those terms mean in the context of different artistic styles, right? So what looks like at sunset is much different than it looks like during the day, right? And actually, they released a version of this, so let's take a look at how this works. So here is GAN running downstairs. It was packaged into something called NVIDIA Canvas, which you can download. And so here, the idea is that you just kind of like sketch out, okay, let's put some grass down here. And right now, since it's a blank canvas, I just have like this blank sky, but as soon as I click something in, it will automatically populate with grass and sky, right? And the style image it's using here is this kind of like sunset image, but if I were to click on another image, I would basically have the same grass and sky scene rendered in different styles, right? So the idea is that you as a user can decide what is the kind of basic style that you want, and then you can kind of keep on sketching to say, okay, now I want to put some trees over here. You don't have to be an artist to make this work, right? So here's a nice tree. Toss some water in here. Toss some flowers along the bank of their thing. Toss some mountains in here. Off in the distance. Maybe I should be a little more careful about this mountain being so close. And then, and I can still just like toggle through different styles, some of which are more convincing than others, right, to get a final image, right? And of course, of course, the machine downstairs is pretty good, but it's working in real time. And, it's pretty cool, right? So this was, of course, a big wave also when it came out. I definitely have seen Instagram influencers or creators using this to make cool videos, right? And so what was the kind of key stuff under the hood of this, right? So the network architecture is very similar to Pix2Pix. So similar architecture. As Pix2Pix. Because remember that Pix2Pix could also do this kind of paint by numbers application. The key contributions, at least as far as I can tell, are a better way of normalizing things that made the results more conformal to the segmentation mask. So a better way of doing normalization. And then, like I said, the way that they provided to use this kind of like style encoded vector to influence the output. So this kind of style vector, which is in the canvas example, coming from just a provided image, which you can also provide yourself. The idea is that you kind of take that style, you encode it maybe using a VAE into some other vector, and you provide that as auxiliary input into the GAN to produce the result, right? So the paint by numbers part and the style part are kind of decoupled, which is kind of neat. Okay, so comments or questions on that? Okay, so I want to talk about art stuff now. I will say that this kind of like coming up to 2020, like 2017, 2019, was really, I think, a tipping point in terms of when it was possible for artists to just take code bases off GitHub and make crazy things, right? Without really, not necessarily needing to understand all the underlying details of how everything worked, right? And so this also led to lots of apps and stuff. So I think last time I mentioned, Face App, right? So, here's a example of what I'm going to look like in hopefully many, many years, right? So again, this is a combination of image GAN stuff as well as this kind of like finding directions in the latent space that correspond to attributes, right? So if you train a certain GAN, like style GAN, you can learn where things are going to go if you want to make the person look older, right? And so, it's all fun and games until you start to come up against some of the more like ethically questionable issues, right? So like these apps, for example, there was a bunch of apps that would make you look hotter, right? So like, what does that mean, right? Is that kind of like a cool thing to do, right? And also what is that kind of is implicitly reinforcing a lot of stereotypes about what hot people look like in different cultures, right? So like, that's not something that I think is great to encode into an app that people use. Is it kind of ethical or cool to make people into different races or different genders via, these kinds of image-to-image translation? I think that's a little bit questionable. And of course, we've already talked a little bit about like, as you're finding directions for these changes that you could use in an app or a program, are those directions labeled correctly? Are they labeled appropriately? Is it even possible to label them, right? So some of these attributes that you see in some of these data sets, like the Celeb A data set, has labels like attractive, right? That's certainly a value judgment. Or heavy makeup, or chubby, right? These are all like kind of really value judgment type of attributes that some random labeler that you don't know who labeled it, and now you're kind of forever like, tagged with this attribute, right? So, I think that there's a lot of questions about like, once the code is out there and once you've got these labels that kind of are, coming from a unknown provenance, right? I think there's lots of things to talk about there. And so actually, I'm thinking about maybe one of the things that I want to do on one of the homeworks is for you to kind of, give me your feedback about, like, after you've seen some of the stuff we're talking about, like, where do you stand on some of these ethical issues that we've seen in some of this image generation stuff? And of course, this is not even to touch on the ethics of like, where did all this training data come from, right? So, all the lawsuits about scraping Flickr and other places, like people didn't consent to having their data used to train these algorithms, much less to be labeled in a pejorative way, right? So, yeah, so it's very tricky. I just saw actually this morning, not quite related, but apparently just today, like Getty Images, who is suing Stable Diffusion for using their images without consent, is releasing their own AI image generator that's trained on all of their proprietary images, right? And maybe when you upload your image to Getty Images, you're consenting to this, but maybe people who upload it to that are not aware that that's now what they've consented to, right? So it's a whole ethical minefield. Okay, so what I want to talk about a little bit now are some artists that have been working with GANs, right? So, this is not an exhaustive list, and certainly not all of the authors, not all the artists I'm talking about are GAN-only artists, right? They do all sorts of other stuff too, but these are some notable people who have used GANs in their work. So, and it's interesting to see like where these people have come out of, right? Some people have come out of the fine art world and are now learning how to GAN and make art with it. Some people are coming from like a CS techie background and are kind of like playing with things and becoming artists. And some people are just like totally, well, as I'll say an example, you know, like there's this one guy, Robbie Barrett, who is basically like he came out of high school playing with these things, right? And I don't know that he would have considered himself a major artist at the time he was in high school, but he certainly has become one as a consequence of just learning how to play around with these tools, right? So the first one I want to talk about is Helena Sarin, who got a CS degree from Moscow, and she worked in the tech world, and she trains GANs with her own artwork, and then things like drawings and paintings and photography. So the stuff that she's able to produce with her GANs is much different than the stuff that comes out of training a GAN on ImageNet or something like that, for example, because she's really curated what goes into the GAN. And again, that's kind of one of the reasons I wanted you to do your own data curation in homework 1, was to be intentional about kind of what goes in, so you kind of recognize pieces of what comes out, right? And so this stuff doesn't really look like the standard data sets. This is one that I particularly like. So this is a collaboration with another artist, Dmitry Cherniak, right? So the one artist makes these super cool, abstract kind of like lines and shapes, and then Helena Sarin took these shapes and kind of put them into a GAN to produce things that are kind of like evocative of those results, right? And so one thing that's a big difference between an artist's approach and a computer science student's approach is that the goal of the art is not to, for example, train the GAN to convergence so it's able to make great reproductions of the input, right? So certainly here, these results on the right-hand side are not like great exemplars of the stuff on the left-hand side, but they are interesting and evocative, right? So the artist is always choosing, okay, when do I like stop my GAN training, right? Or how do I tweak this thing to make a result that I think looks cool, right? The goal is not photographic fidelity to the input, right? The goal is, kind of like opening the box and playing around with intermediate stages of the results, right? And then also, this artist in particular, Helena Sarin, does a ton of, kind of more traditional digital art, right, in terms of like layering and collaging and remixing. So what comes out of the GAN is not necessarily the immediate end product. It's used as further input to further processing, right? And so this is a project called VGAN, which I guess was trained with pictures of lettuce leaves, right? So we have a bunch of leaf enthusiasts in this class apparently, so you might like this. But if you zoom in on these, there's some interesting like structure to these lettuce images that's kind of like angular and interesting to me. I mean, you can't really see it on where you're sitting, but like if you look at her project, I think that those images are pretty cool to look at. Another person that certainly I've been following on Instagram for a while is Sophia Crespo. And so she I think, came up in the art world. I believe she's from Argentina, but she works in Berlin and Portugal. And so much of her work is biologically inspired. And again, same as Sarin, she is training custom networks on data that she's collected herself. So she's not just using the off-the-shelf, off-the-shelf GANs. And the results are kind of like, she does things with birds and jellyfish and flowers and so on. And I think the results are really cool looking. And some of the favorite stuff of hers that I like is, kind of training on these kind of like older books of like, you might have a naturalist who sketched birds and plants and stuff by hand and kind of feeding those into a GAN and producing these kinds of like sketchbooky looking results, I think are really neat. And so if you look at her Instagram, so let's take a look for a second here. So I put links to kind of representative stuff on here, but her Instagram has lots and lots of examples of cool looking things, and her, she's had it, in Times Square and so on. So you can see that this is largely kind of like biology and living creature inspired kind of stuff. And I think the results are really interesting. And I think that the underlying thing for most of this stuff is indeed GANs. So let's see. So another kind of famous GAN artist is Mario Klingemann. So he, trained GANs on, like oil portraits, and then made this kind of video exhibition. So you can kind of see that what's happening here, for example, is kind of like zooming in and translating between objects in the latent space, right? And if you look at his website and his Twitter, for example, let's just take a look at that for a second. So I don't think that the Twitter has been updated very recently, but his website is quasimondo.com. Well, let's see here. So if you kind of poke through his posts, you see something where he's kind of always playing around with what does the GAN do, and what can well, I'm going to show you this in just a second. This kind of is like a pix-to-pix thing. Taking live feed, again, so if you've got this like image-to-image translation thing, you can get it working in real time on a webcam and make these kinds of, turn your face into oil painting in real time, right? And so his Twitter is a good, this is also kind of cool, like, training like this kind of older, timey looking, to me this looks like celluloid kind of film, right? So yes, I suggest, kind of like just poking around like what these artists are doing. One thing that I think that he did that I like, I'm not sure exactly what the title of this piece technically is, but I think it was called neurography, right? So it's like photography, but with neural networks, right? And so here's a case where you can imagine this is kind of like a pix-to-pix thing, but the output is kind of like these images that you might get from like electron microscopy scans of something, right? This kind of cool, super contrasty, almost like an X-ray, of an object, right? So it's kind of like photographing in the latent space, which I think is really interesting. So I mentioned this. This guy, Robbie Barrett, right? So Robbie Barrett started as a high schooler in West Virginia in 2017 and started to train his own GANs on image databases from museums and classical portraits and microscope images and stuff like that, right? So this is an example, again, similar to the one I showed you before, where he hooked up with an artist who draws all sorts of skulls in different ways, and then he trained a GAN on these skull images to make these kind of GAN-generated skulls that look like what the artist did. And so I'll come back to him in just a second, but like, again, when I was a student, it was impossible to imagine to be that some high school kid would take my research code and generate cool-looking stuff with it. It just didn't seem possible. But now, if you're willing to put your stuff on GitHub, you never know who's going to use it for stuff. So the next one I want to show you is called Learning to See, Gloomy Sunday, and the artist is called Memo Acton. And here's a great example of like pix-to-pix, but done where the input image is a human that is in real time moving pieces of cloth around underneath a webcam and generating on the fly this kind of cool, photographic result, right? So it's like you can simulate the waves crashing around by moving these two pieces of cloth around under a webcam, and you instantly get this kind of very compelling result, right? And so we don't have time to watch the whole thing, but like, it's pretty crazy. Like now we've got this adapter that's taking the shape of mountains, but if I were to change the adapter's function, now it's like a lava, situation where I've got, apparently this fiery scene, right? I think it's just really cool that, now we've got this playing the role of clouds in the sky, right? And here, this is like flowers, right? So this was in 2019. Again, I think it's like very compelling and fun to fool around with this stuff, right? And something that probably the original creators of the software would never have thought of to do or to think of necessarily as art, right? So one of the highest profile GAN art situations, although not necessarily maybe for the right reasons, was this famous auction that rocked the art world, right? So this is a French artist collective called Obvious, 3 French guys. And so they sold this painting at auction. And so this is an entirely GAN-generated image. And so if you look, instead of like the signature of the artist, instead they kind of signed it with the GAN loss function, right? And so it was kind of cheeky. And so they put this on sale for, the asking price of this thing was something like $8,000, something like that. But it ended up selling for almost $450,000, right? It was one of the first GAN art pieces to come up for auction, and someone paid a huge amount of money for it, right? But then it became clear that they had actually used this public GAN code that the high school I told you about, Robbie Barrett, had created, right? So he had created a GAN that made these kinds of like realistic looking paintings. And so it's not a very long stretch from this to this. And now that brings up real questions of like, ownership and provenance, right? So like, you know, did the GAN create the art, or did Robbie Barrett create the art, or did this French collective make the art? Like, you know, who does it belong to, right? Did the computer do it on its own somehow? And so I encourage you to read the whole story. So I linked to it on the webpage. So here, if you go back to the story of the portrait of Edmund Bellamy, kind of tells the whole story of, and I think this was actually even before it sold, right? So at the time, they were thinking it was going to sell for $7,000, but it sold for like, you know, mass multiples of that, right? But it does go into the kind of controversy of like who should be responsible, right? Because in the beginning, these artists didn't necessarily disclose that that's where their code came from, and then people started pointing it out, and they were like, okay, yes, you know, we talked to this guy, but they didn't necessarily credit him, and so it was a huge, you know, kind of like art world controversy, right? And I think that also, we're gonna kind of come back to this idea when my friend Aaron Hertzman talks to us about like, can computers create art, right? So I'm sure he'll probably talk about this situation in his talk too. So also around this time, Jason Salivan, who was a fine artist, you know, at the University of Chicago via, I think he started in the video game industry, but he basically, you know, became a fine artist. You know, this is an example called Genmo or Genmo and YGAN, right? So if you look at his, you know, his kind of website, you can see that he's done a large amount of stuff, right? This is not the only thing, and most of the stuff he does is not GANs, right? But this was kind of like an early, let's see if I can find it here. I saw it earlier. Oh, I remember he did this too. This is something I always liked. This is called the top grossing film of all time, which is actually just like taking every frame of Titanic and showing it as one square of color. And you can kind of read the image over time as like, okay, it's nice and sunny, and then we get to the sunset, and the ship sinks, and everything is dark, right? So that's one of his non-GAN works. And I guess he kept on doing similar things. So where is the thing I'm looking for called GANMO? Oh, here we go. Right. So this is clearly a GAN system. And I think that, you know, there was this kind of, like he says, you've seen photo mosaics, right? So there was definitely like a kind of a trendy thing to do, like where you could make like, you know, whatever image you wanted out of like license plates or flowers or whatever, right? You could take all your pictures and you could step back, and when you step back, you see this kind of like revealed picture. So the idea was to kind of do similar things, but with, you know, you take a photograph and then you turn it into a thing that's made entirely out of flowers, right? Or this picture is made entirely out of clouds, or this picture is made entirely out of pieces of old master paintings, right? So this was, again, 2017, right around the time when all of the, you know, generative architectures were becoming easy for people to use. Another landmark thing, which unfortunately I don't think exists in the same way anymore, was called GAN Breeder, right? So GAN Breeder was a lot of fun to play with back in the day, where the idea was it was definitely using a GAN under the hood, but it didn't really exactly expose how you were using it. Instead, what you did was you kind of selected images that you liked that the GAN was able to generate, and then you kind of like mashed them together and made other images. So I think that probably it's not that different than we talked last time about style GAN, right? The way you could take the style vector from one image and the style vector from another image and to kind of have this crossover point. I think that may be partially what's going on here, right? We could say, okay, I've got, you know, the style vector from a daffodil and the style vector from a dog, and I can produce the image that I see on the right, right? We were looking at style GAN from the perspective of trying to mix images of the same class, but GAN Breeder was using it to mix images of totally different classes. So what you could do is you could kind of like have these slider bars where you could select how much dog do I want, and how much flower do I want, and how much randomness do I want. And then you'd make these crazy looking images. Some of them look good and some of them look weird. But unfortunately, I think that if you go to the GAN Breeder website now there's something called Art Breeder, which I think is by the same person, but I can't quite see exactly where in the Art Breeder interface you can get to this old GAN Breeder thing. So I'm not sure this is still something that you can play around with yourself. And then the final thing I want to talk about was Rafiq Anadol. So he's a more modern kind of like machine learning based artist. One of the things that he famously did was to train, I want to say GANs, but he certainly trained generative models on like all of the images in the MoMA in New York's collection, right? So one of the things that you can do if you go see the MoMA is there is this huge display wall that you see people sitting in front of like it's a church. It's something to see, actually. So like it's a massive display wall that is cycling through like different generative models. Like this, for example, is not even generative. I think this is just like a fluid simulation that looks super cool at big scale. But then sometimes it will transition into a phase where it's kind of showing these blobs of color that clearly are inspired somehow from different things in the MoMA collection. And then it will kind of go back to do different things. So if you ever go to the MoMA, this is like on the entry floor. I think you do have to pay to see it. It's behind the paywall, but it is worth seeing. And one thing that I'm always amused by is like sometimes the display will switch to like this techie, dashboard where it says things like 0 crossing rate, energy difference, peak energy, convolution weights, and of course like maybe to like someone who doesn't know what those words mean, it's like, oh, this is super cool and techie. But to someone who actually understands what these things might mean, it's kind of funny to see on this big screen and people looking at it like, wow. So yes, so this is Rafiq Anadol in his studio. I would say, like I said, I'm not sure it's 100% GAN. Certainly there are non-GAN things in there, but it's certainly generative based on the MoMA's work, right? And so maybe Aaron will say more when he talks to us. I think that clearly, like the late 2010s were this sweet spot for people using GANs to make, I think art in the sense of like kind of capital A art, right? Like these people who are making these works are kind of established as artists, right? I don't think that you're getting the same sort of wave of people who are using like Stable Diffusion or Midjourney to make art. Like I don't think that there's a yet wave of fine art coming off of that kind of thing. Maybe partially because it's just too, or it can be just too perfect, right? Like you put the prompt into Midjourney and it looks great, and of course you don't necessarily have that much access to what's in the middle, right? I think that the only place where you'd get that is probably in Stable Diffusion, where you could actually, in theory, try to get into the guts of it because you have the source code, right? But I haven't necessarily seen yet the next great like diffusion-based artist, right? So we'll see. All right, so let me pause to ask any questions or comments about that. Given my limited knowledge of the art world, this is my 20-minute overview of some of the stuff that I know about, at least. I think we'll hear about other things too. Okay, so with that, let me stop the recording.